Hello students, today we are going to discuss about ray optics and optical instruments NCERT section 9.1 to 9.2.2. So this is the disclaimer. Strategy for comparative exams. So focus on understanding the fundamental principles of ray optics and image formation by mirrors and lenses. Learn the mirror equation, lens equation and lens maker's formula with proper sign conventions. Master the concept of total internal reflection and its application in optical fibers and prisms. Practice ray diagrams for different positions of objects with spherical mirrors and lenses. Study the working principles of optical instruments like microscopes and telescopes. Understand refraction through spherical surfaces and combination of lenses. Please visit https://forum.pruter.ai for book recommendations and guidance. So after this lecture, you will be able to understand the fundamental properties of light, historic perspectives of light study, and the basic principles of ray optics. So today we are going to discuss the introduction part and the mirror equation. Okay, mirror equation we are going to discuss in the next chapter, sorry, but today we are going to discuss about the geometrical representation of spherical mirrors, okay, and sign conventions. Also we are going to discuss about the relation between focal length and radius of curvature. Concept of spherical mirrors including sign conventions, focal length calculations and their practical applications in optical systems. So index of topics that we are going to cover today: 9.1 section of NCERT introduction, NCERT section 9.2 reflection of light by spherical mirrors, NCERT question 9.2.1 sign convention, and NCERT section 9.2.2 focal length of spherical mirrors. So let's begin with the introduction. So nature has endowed the human eye with remarkable sensitivity. Okay, our human eye can detect only which region of electromagnetic spectra? Only visible region. That's why it is called visible. Okay, only that region our human eye can detect. Okay, so nature has given the human eye with remarkable sensitivity to detect electromagnetic waves within a specific range, and that range is called visible range of the electromagnetic spectra, means 400 nanometer to 750 nanometer, to which this range we can say we can detect this range, we can see the visible light. This electromagnetic radiation with wavelengths approximately from 400 nanometer to 750 nanometer. So for this range our human eye can detect this range of electromagnetic waves, constitutes what we call visible light. Light serves as our primary means of perceiving and interpreting the world around us. Okay, everything we are seeing, everything we are interpreting by seeing. So it is very important sense. Okay, without eyes we can't do anything. So the light serve as primary means of perceiving and interpreting the world around it. Okay, so light falling on any objects after reflection comes to our eyes, and our eyes detect the object and our brain process it. Okay, so for vision purpose there should be light. We cannot see in darkness properly because there is no light. So light is required to perceiving and interpreting the world around us through the sense of vision. Study of light phenomena has attracted scientists and philosophers for centuries. Okay, light has been in the world from beginning. Okay, without light there is nothing possible. Okay, so study of light, what is its properties? Okay, to develop various optical instruments. So the study of this light phenomena has attracted many scientists and philosophers for centuries, leading to important discoveries for concept of light phenomena. Also development of various optical instruments like telescope, microscope, okay, lenses, these type of optical instruments that are being used nowadays They were discovered or invented after studying the light phenomena. So what is historical perspective on light? So development of ray optics by scientists like Euclid or Ptolemy laid foundation for geometric optics. Okay, what is geometric optics? That we are going to discuss in ray optics. We are going to make some ray diagrams. Okay, we are going to discuss about the working of optical instruments. Okay, by drawing the ray diagrams. Okay, so that is geometric optics. Okay, so scientists like Euclid and Ptolemy laid foundation for this geometric optics. Medieval Islamic scholars like Ibn al-Haytham made significant contribution to understanding light propagation. Okay, so how light propagate through different mediums, how light propagate through vacuum. Okay, light is also an electromagnetic wave. So its behavior is similar to electromagnetic waves. Okay, so how any electromagnetic wave travel in vacuum as well as medium. Also, how light can travel through vacuum or medium. Okay, so study about these concepts or these questions were made. Modern understanding emerged through the work of scientists. So after the optics, we are going to discuss the wave optics. Okay, so light exhibit both nature, particle nature and wave nature. So we are going to discuss its wave nature in upcoming unit. So modern understanding of optics or modern understanding of this light phenomenon that were given by Newton, Young and Maxwell. Maxwell discovered the electromagnetic waves. He gave theory about electromagnetic waves and he proved or he showed that light is also an electromagnetic wave. Okay, then Newton studied some phenomenon, and Young, you will learn about Young's double slit experiment in wave optics. Okay, so modern understanding emerged through the work of these scientists, Newton, Young and Maxwell. So what are the fundamental properties of light? Light travels with enormous speed in vacuum. So in vacuum, because light is an electromagnetic wave, so light travels with enormous speed in vacuum, that is C equal to 2.9979248, and this value we approximately take 3 into 10 to the power 8 meter per second. So for more practical purposes, okay, we cannot use this value with high amount of decimal places. Okay, for calculations or for complex problems or for practical purposes, we use the approximation, that is C equal to 3 into 10 to the power 8 meter per second. Speed of light in vacuum represent the maximum attainable speed in nature according to Einstein theory of relativity. Okay, so Einstein gave the theory of relativity. So he told that speed of light is maximum attainable speed in the nature. Okay, no object can have more speed than the speed of light. Okay, in vacuum. So light exhibits both wave nature and particle characteristics, a concept known as wave particle duality. Okay, so light exhibits both particle nature, wave nature. Wave nature we are going to discuss in wave optics. Okay, so that concept was known as wave particle duality. Okay, or particle nature is due to the, in particle nature we discussed that electromagnetic waves or light, it consists of small packets of energy that are known as photons. Energy associated with a photon of a specific electromagnetic wave having frequency nu is given by E equal to h nu. Okay, it is also showing wave nature, in which electric and magnetic fields are mutually perpendicular to each other and they are time varying electric and magnetic field. They are mutually perpendicular to each other and perpendicular to the direction of propagation of wave. So what is the ray approximation? So when light wavelengths are very small as compared to dimensions of obstacles and aperture. What is aperture? A small opening through any sheet or any object, small opening. It is called as aperture. Okay, so if the size of aperture through which light is passing or any obstacle through which light is passing, if dimensions of these obstacles and apertures are very, very large as compared to the wavelength of light, then we can treat light as the traveling in straight line. Okay. And light is traveling in straight lines, but light is a wave, so electric and magnetic fields which are in the which constitute the light, which is also an electromagnetic wave, they are sinusoidal and varying with respect to time. But we consider light as an straight line, that light is traveling in straight line, because we in ray optics we assume the dimensions of obstacle and apertures. We are using some lens through which light is passing. Okay, there is some aperture, okay, small opening through any material. Okay, we are like slit. Okay, slit is also considered as aperture. Okay, so dimensions of obstacle and apertures we consider in ray optics to be very large as compared to the wavelength of light. So these straight lines path are called ray of light. So light travels in straight lines, and this straight line path is called ray of light. A collection of rays, number of rays collected in a bundle type, it is called beam of light. Okay, so collection of rays form a beam of light. Rays do not disturb each other upon intersection. Okay, so if two rays of light are intersecting each other, they do not disturb each other. Okay, they do not change the path of each other. So ray trace back their path if their direction is reversed. At any point, if direction of ray is exactly or directly reversed, okay, it is exactly reversed at any point, it will retrace its path. Okay, it is coming from any source after number of reflections or refractions. The path or direction of the ray is exactly reversed, so it will retrace its path to the source from which it is generating. Okay, that is called principle of reversibility. What is scope of ray optics? So ray optics deal with propagation of light through homogeneous medium and across interfaces. Interfaces means the any face that is separating, any surface that is separating two medium. Okay, two media, like there is a slab, okay, and it is placed in water. So the surface of slab that is separating the water and material of slab is glass, that is separating two media is called interface. Okay, so homogeneous media. So ray optics deal with the propagation of light through homogeneous media and across the interfaces. It confines phenomenon such as reflection from plane and curved surfaces. Okay, from plane mirror, from spherical mirrors, from any type of surface. Refraction through different media. So media is the plural of medium. So refraction through different media, dispersion of light into constituent colors. Okay, so white light is formed from 7 colors. Its constituent color are 7. Okay, so dispersion of light into 7 constituent colors. Formation of images by mirrors and lenses. Working principle of optical instruments. Okay, optical instrument we are going to discuss microscope and telescope. Okay, that optical instrument we are going to discuss in detail. So working principle of optical instrument, formation of images by mirrors and lenses. So application in modern technology. So optical fibers, okay, that are used now for high speed network. Okay, if you want to use high speed network, then many people take service of optical fibers. Okay, they are very thin, like hair, like human hair, like thin fibers that are used to transmit, that are used for telecommunication or for network. So optical fiber communication rely heavily on principle of ray optics. Camera systems and photographic equipment utilize lens combination based on ray optics. Medical instruments like endoscopes. Endoscopes are also made of optical fibers. Okay, so with the help of optical fiber, endoscopy is done. Okay, it is the diagnosis of internal organs. A fiber is inserted into your mouth to examine your internal organs. Okay, and that endoscope use fiber optics for internal examination. Laser technology applications in manufacturing and medicine. Astronomical telescope for space exploration and research. Also, microscopes are used to research. Okay, in biology, microscopes are used to see the different type of microorganisms. Okay, different type of cells in our body. Or microscopes have many vast applications in other fields also, to see the grain structure, like we have discussed about in magnetism and matter. We discuss about the domains. Okay, we have discussed ferromagnetic substance, in which domains were there, grains were there. Okay, to visualize that grains or visualize that domains, high resolution microscopes are used nowadays. So let's start with law of reflection. Okay, so this diagram, figure 9.1, the incident ray, reflected ray, and normal to the reflecting surface lie in the same plane. Okay, this is the one of the law of reflection. Okay, so you can see in the diagram, mirror is there, incident ray is coming, and after incidenting on the mirror, it is reflected. So incident ray, reflected ray, and normal is being shown. Normal is the perpendicular line on the mirror, which is perpendicular to the plane of mirror. Okay, so angle of incidence is the angle between incident ray and normal. Angle of reflection is the angle between normal and reflected ray. Okay, so fundamental laws governing reflection of light are universal and apply to all reflecting surfaces. First law, the incident ray, reflected ray, and the normal to the reflecting surface at the point of incidence all lie in the same plane. You can see the gray part. This gray shaded part is the plane. So incident ray, reflected ray, and normal to the point of incidence, they all lie in the same plane, this gray plane. Okay, this is the first law. What is the second law? The angle of incidence equals to the angle of reflection. So this angle of reflection, which is the angle between incident ray and normal, is equal to the angle of reflection, which is angle between the normal and reflected ray. That is, angle of incidence will be equal to angle of reflection. These laws were first systematically stated by Euclid and later refined by Hero of Alexandria. These laws are valid at each point on any reflecting surface, whether plane or curved. So these laws are valid for plane surface also and curved surface also. Okay, or irregular surface also. So law of reflection are valid everywhere. Okay. So we shall restrict our discussion to special case of curved surface, that is spherical surfaces. Okay, we will discuss the spherical surfaces or spherical mirrors. So we will restrict our discussion to the special type of surfaces, that are curved surfaces. Like this is figure showing the normal in case of spherical surfaces. Okay, if in plane surface we draw the normal which is perpendicular to the plane of mirror, in case of spherical mirror, what we can do, at the point of incidence where ray of light is incidenting on the mirror, okay, we draw tangent there at that point of incidence. This is point of incidence, we draw the tangent of this convex mirror, and perpendicular to this tangent, this is normal for spherical surface. Okay, so this is tangent to the surface, this is convex mirror, and this is ray of light incidenting on a certain point, and we can draw the normal line at that point perpendicular to this tangent. Okay, the normal in this case is to be taken as normal to the tangent of the surface at point of incidence as shown in the figure. That is, the normal is along the radius, the line joining the center of curvature. So what is center of curvature? So this is a part of a sphere. This mirror is a part of sphere. So that sphere will be having some center. Okay, this mirror is a, this convex mirror is a part of any sphere. Okay, so it will be having some center, that is center of curvature. From that center of curvature to the outer part, that is radius. So this normal line, this is along the radius, and it will meet at center of, it will pass through center of curvature of the mirror of, okay, to the point of incidence. Now figure showing the geometric properties of spherical mirrors. So let's see the geometrical properties. A spherical mirror is a section of hollow sphere. So these are hollow spheres. So these spherical mirrors are some section cut out from the hollow spheres, hollow glass spheres. Okay, with one surface polished. So what is convex mirror? Its internal surface is polished and its reflecting surface is curved outwards. And for concave mirror, its reflecting surface is curved inwards, and behind it, it is polished. Okay, a spherical mirror is a section of hollow sphere with one surface polished to act as reflecting surface. Concave mirrors have their reflecting surface curved inwards. So this is concave mirror and their reflecting surface is curved inwards, and outwards there is a polishing. Okay, towards the center of the curvature. Okay, so their reflecting surface is towards the center of curvature. So center of curvature is there. So their reflecting surface is towards the center of curvature. Now convex mirror have their reflecting surface curved outwards. So their reflecting surface is outwards and inward surface is polished. Okay, so the reflecting surface is away from this center of curvature. So their reflecting surface is curved outwards. So they are away from the center of curvature. Or in the case of concave mirror, reflecting surface is towards the center of curvature. Okay. Pole. What is pole? Is the geometric center of the spherical mirror. So this is the mirror and its geometrical center. It is called pole. Okay. It is given in the diagram. Now, what is principal axis? It is a straight line joining the pole to the center of curvature. So joining pole to the center of curvature and then extend on both sides. This is principal axis of the mirror. What is center of curvature? Is the center of sphere from which mirror is cut. So this is the actual sphere and a part of this sphere is cut out to be mirror. Okay, so it is the center of the sphere from which this mirror is cut. So this is the center of curvature of this mirror, and for this concave mirror, this is the center of curvature. What is radius of curvature? It is the distance between the pole and center of curvature. So distance from pole to the center of curvature is called radius of curvature. So it is the radius of the sphere from which mirror is cut, we can say also. Okay, now the Cartesian sign conventions. So sign conventions importance. Consistent sign conventions are essential. Consistent means standard or not changing. Sign conventions are essential for solving mirror problems systematically. So Cartesian sign conventions provide a universal approach for all the mirror calculations. So we have to follow some sign conventions that are applicable for all mirror calculations. Okay, so you can see in the diagram, figure 9.2, there is a incident light. So direction of incident light is given. It is from left to right, falling on mirror. So distance against this incident light will be taken as negative, and distances along this incident light measured can be taken as positive. So understanding sign conventions prevent the error in determining image characteristics. Okay, so we are going to determine whether image is real, virtual, okay, where is the image formed. So for that we have to follow some sign conventions for the calculation. So the Cartesian sign convention, all distances are measured from the pole. Okay, this is the first rule. This is a pole, this is the pole, it is a geometrical center of mirror. Okay, so all distances are measured from the pole. Okay, whether it is image distance, whether it is focal length, whether it is radius of curvature, whether it is object distance. So all distances are measured from the pole of the mirror along the principal axis. So distances measured in the same direction as incident light are taken as positive. Okay, so distances that are measured, if we are going to measure some image distance, and image is formed behind the mirror, so we are starting from the pole and going towards the image formed. So it is along the direction of incident light. So it will be taken as, that distance will be taken as positive. If we have placed some object in front of mirror and we are measuring from the pole, we are going from pole to the object. So distance measured from pole to object is distance measured in the opposite direction of, or in against the direction of incident light. So it will be taken as negative. Okay, so distance measured in the same direction as incident light are taken as positive, and distance is measured opposite to the direction of incident light are taken as negative. Okay, heights measured upward from the principal axis are positive. Okay, height above the principal axis will be taken as positive, and heights below the principal axis are taken as negative. Okay, so these sign conventions are applicable for all type of mirrors, for convex, for concave and plane. Heights measured downwards from the principal axis are taken as negative. Detailed sign convention rules. For object distance, u, object distance is denoted by u. So object placed in front of the mirror, that is real object. When object is placed in front of the mirror, it is considered real object. Okay, so u is taken negative. Why u is taken negative? It is placed in front of the mirror. So we are measuring from pole. We are measuring from pole to the object. Okay, so we are going from against the direction of incident light. So object distance will be taken as, so real object distance always will be taken as negative. Object placed behind the mirror. So how can we place object behind the mirror? It is not possible. So that object is virtual. That means rays of light are coming from, so if we have placed some another mirror or lens in front of this mirror, so image formed, this mirror is coming in the way of that lens or mirror and the image, due to which that image formed by that lens or mirror placed in the front of this mirror will be taken as object of this mirror, which will be formed behind the mirror. That is called virtual object. Okay, so object placed behind the mirror is virtual object. In that case, u is taken positive. For image distance is represented by v. So image formed in front of the mirror, that is real image, v is taken negative. Okay, so if image is formed in the front of the mirror, that image will be real image, and v is taken negative because we are measuring from pole. Image formed behind the mirror. If image is formed behind the mirror, so we will start measuring from the pole to the image. So we are going in the direction of incident light. So then v is taken as positive if it is formed behind the mirror, and it is called virtual image in that case. For height, erect image, if image is erect, it means it is above the principal axis. So height is taken as positive. If it is inverted, it is below the principal axis like this, height downward. This is inverted. So it will be taken as negative, and high upward it is taken as positive. So the any image or object that is above the principal axis is called erect image. Any image which is below the or in the downward direction of or in below the principal axis is called as inverted image. That is virtual. Sorry, that is real. Advantages of consistent sign conventions. So single formula works for all type of mirrors, concave and convex. Okay, we are going to derive the mirror equation in our next lecture. So that formula works for all type of mirrors if we are using the sign convention. We don't have to modify the formula. Formula will be remain same. According to sign convention, we will determine different type of mirrors. And according to that mirror, we will put the value for U, V and F and find the required thing. Eliminates confusion between different cases. Ensure consistency across different optical systems. Okay, for mirrors, lenses, okay, or any other optical system. So they ensures consistency. If we are following sign convention, we don't have to modify the formula again and again. So common sign convention mistakes that students do in the exams. So that is forgetting that object distance is typically negative. So real objects, object distance will be taken as negative. If we generally place object in front of mirror or lens, so object distance will also be always be taken as negative for real objects. Confusing the direction of measurement from the pole. Okay, we are measuring everything from pole. You cannot measure the distance of image from image to pole. No, you have to measure the distance of image from the pole to the image. Incorrectly applying signs to focal length and radius of curvature. So we are going to see that what are the sign of focal length and radius of curvature for two type of convex or concave mirrors. So mixed application of different sign conventions in the same problem. Okay, so due to mixed application of different sign conventions like height and direction of incident light, so all applications of sign conventions in same problem, it will create the confusion, and due to confusion it will lead to mistakes. Okay, now focal length of spherical mirrors. So definition of principal focus. What is focus? It is represented by figure 9.3, focus of a concave and convex mirror. So when a parallel beam of light, so you can see in the diagram, there is parallel beam of light. Okay, in both cases, this is a convex mirror, this is a concave mirror. Okay, so parallel beam of light. When a parallel beam of light rays parallel to the principal axis strikes a spherical mirror. Spherical mirror means convex or concave. Both are spherical mirrors. The reflected rays either converge. In this case, in concave mirror, the reflected rays will converge at one point or appear to diverge from a specific point. So this, in the case of convex mirror, they do not converge, they diverge and appears to meet at specific point, or we can say appear to diverge from a specific point, like this. If we extend the diverged reflected rays, we will extend them behind the mirror. They will meet at one point and it looks like that these reflected rays are diverging from a specific point. So that point is called focus of the mirror. And in the case of concave mirror, these rays are actually converged and met at one specific point, that is called focus of the mirror. So this is the focus of concave mirror, this is focus of convex mirror. So this point is called principal focus F of the mirror, or simply it is called focus. The distance between the focus and the pole is called focal length. So distance measured from the pole to the focus, distance measured from pole to the focus is known as focal length. Now, you can write in the comment section, focal length of concave mirror is positive or negative? We are measuring any distance from the pole. So focal length of this concave mirror is positive or negative? How? It is negative because direction of light, incident light is from left to right, and we are measuring from pole to focus. We are measuring from right to left. Okay, so focal length of concave mirror is taken as negative, and focal length of convex mirror will be taken as positive because we are measuring from pole to focus. So we are measuring in the direction of incident light. Okay, so focal length for convex mirror will be positive. Okay, here is focal plane. So when a paraaxial beam, what is paraaxial? Two type of beams are there, paraaxial and marginal. Paraaxial means beam closer to the principal axis. So when rays of light are very close to principal axis, then they are called paraaxial beams or paraaxial rays. When rays are farther apart from the principal axis, or they are incidenting on the edges of the mirror, they are called marginal rays. Okay, so in our chapter we generally deal with paraaxial rays or paraaxial beams. We are not taking into account the marginal rays or marginal beam. Okay, so when a paraaxial beam closer to the principal axis of light rays hit a mirror at an angle, you can see in the diagram, this parallel beam is not along this is a parallel beam, but it is not parallel to principal axis. It is at some angle to the principal axis. Okay, when a paraaxial beam of light hits a mirror at an angle to the principal axis, these rays will either meet at a specific point or seem to come from a point. So they will meet at a specific point after reflecting. Okay, so it is how they are reflecting from this spherical mirror? By law of reflection. Okay, so this from C, this is radius of curvature. So the normal at any point will pass through the radius of curvature. From radius of curvature at that point, it is normal. And this is angle of incidence, this is angle of reflection. So this ray will reflect like that. Similarly, this ray will reflect like that. And at which point they are meeting? Or it will appear to meet in the case of convex mirror. In convex mirror, rays do not meet actually. They appear to meet at some point. This point lies on a flat surface. This is surface, shaded part. This point at which these rays are meeting, this is lying on a flat surface which passes through the focal point F, which is passing through focus, and it is perpendicular to the principal axis, and that plane is called focal plane. Okay, if parallel beam of light is coming at some angle to the principal axis, then after reflection these rays are meeting at some point, and this point lies on a flat surface which passes through the focus and perpendicular to the principal axis, and that plane is called focal plane. So this flat surface is known as mirror's focal plane according to figure 9.3c. Okay, so focus characteristic for different mirrors. So for concave mirror, okay, for concave mirror, parallel rays converge at the focus after reflection. Okay, if parallel rays parallel to the principal axis are coming from a distant object, after reflection they will meet at one point on the principal axis. This point is called as focus. Okay, or if these parallel lines are coming from a distant object, but these parallel lines are not parallel to principal axis, they are at some angle to the principal axis, then image will be formed at focal plane but not at focus. Focal plane is plane passing through focus and perpendicular to principal axis. So image will be formed at focal plane, not focus. Okay, only parallel rays that are also parallel to the principal axis, they will meet at principal axis, and that point of intersection of all the reflected rays on the principal axis will be taken as focus. So parallel rays converge at focus after reflection. Focus is real and located in front of mirror. So this focus is real because these rays are actually converging at one point. Okay, so this focus is real and it is in front of the mirror. Okay, so since it is front of the mirror, so focal length is negative according to the sign convention. Radius of curvature. Radius of curvature is also C. Center of curvature is in front of the mirror and radius is the distance from pole to the center of curvature. So we are measuring from pole to center of curvature. So radius will also be taken as negative because center of curvature in front. Can form both real and virtual images depending on the object position. Okay, so in 10th class we have discussed, okay, you may have discussed in 10th class cases of image formation. Okay, there are 6 cases of image formation of concave mirror. When object is placed at infinity, when object is placed at beyond C, means at some point here beyond C. Second case, when object is placed at C, when object is placed at between F and C, and when object is placed at F. These are 5 cases for which image will be real and inverted. Now, when object is placed between pole and focus, then image will be virtual. So, this concave mirror can form both real and virtual image depending on the object position. Now, for focus of a convex mirror, so parallel rays appear to diverge from the focus after reflection. Okay, so these parallel rays are coming and striking the mirror. So they appear to be diverged from one point called focus after reflection. They appear to be, but not actually. That's why focus is virtual and located behind the mirror. Okay, now it is behind the mirror. We are measuring from pole to focus. We are measuring in the direction of incident light. So focal length is positive according to the sign conventions. Also, radius of curvature is in same direction behind the mirror. So we are measuring from pole to C. So this radius of curvature will also be taken as positive because center of curvature is behind. Always form virtual. So there are 2 cases of image formation. Okay, one is beyond F, other is between pole and F. Okay, so there are only 2 cases for the image formation of convex mirror, and in both cases the image formed will be virtual, erect and diminished. Diminished means small size. Now derivation of focal length formula. So figure 9.4, geometry of reflection of an incident ray on a concave spherical mirror and B convex spherical mirror. Okay, so this is concave mirror, this is convex mirror. So image formation, or we can say geometry of incident ray is given in both for both of the mirrors. Okay, so this incident ray is striking the mirror, both mirrors at point M. Okay, after reflection it will pass through focus, it will appear to pass through focus. Okay, that is the normal from C because normal pass through the center. So that is normal, and normal in the case of convex spherical surface will be that dashed line. Okay, and that theta theta, that is angle of incidence, that is angle of reflection. Both are equal. Okay, and this angle is 2 theta. This angle is 2 theta. Okay, why 2 theta? Because this whole angle is theta plus theta, 2 theta. So this line is meeting here and this line is parallel to this line is parallel to this. So angle, this is 2 theta. Similarly, this is internal angles. So this is that type of Z is forming. Theta plus theta, 2 theta, and this angle will be 2 theta. Okay. So consider a ray parallel to the principal axis striking the mirror at point M. So this is This ray, incident ray, is striking both mirrors at M. The geometry of reflection gives us, let theta be the angle of incidence, this theta. So this is the normal, this is incident ray. So this is the angle of incidence. Similarly for that, this is the normal, this is incident ray. Sorry, this is incident ray. So angle between incident ray and normal will be theta. So let theta be the angle of incident at point M. MD is perpendicular from M. So this MD, throw a perpendicular from M to principal axis at point D. So MD is a perpendicular from M to the principal axis. Okay. For the triangle MCP, so this triangle MCP, okay, or this triangle MCP, okay, in actual triangle is MCD, but this D and P points are very close to each other. We are talking about paraxial rays, means rays very close to principal axis. So this D and P are very close to each other. So we can take MCP. So this angle MCP, in both cases MCP is theta. For triangle MFB, for this triangle MFP, this angle is 2 theta for both these mirrors. Okay, in triangle MDC and MDF. So in triangle MDC and MDF, in both triangles respectively, tan theta. So find tan theta from here. Tan theta will be perpendicular upon base. So tan theta will be MD upon CD. Okay, and tan 2 theta from here will be MD upon FD. So tan 2 theta will be MD upon FD. Okay, mark it as equation 9.1. For paraxial rays, the rays that are very close to the principal axis, so we consider these angles are very small. This is our assumption according to paraxial rays. So rays are very close to the principal axis. So this curvature, this curve is very less significant. Okay, due to which the angles, these angles are very small. Okay, this is our assumption. So tan theta for small angle, sin theta is approximately equal to theta, and also tan theta approximately equal to theta. So tan theta will be equal to theta approximately, or tan 2 theta will be approximately equal to 2 theta. So therefore, theta is equal to MD upon CD and 2 theta equal to MD upon FD. Okay, so tan theta, we have approximated tan theta with theta. So theta is equal to MD upon CD, 2 theta is equal to MD upon FD. So now you can see this MD upon FD is 2 times this, because theta is this MD upon CD. So this MD upon FD is 2 times MD upon CD. Okay, we have reached here. Now, MD upon FD is equal to 2 times MD upon CD. That means this gives us, so MD and MD will get cancelled out. So after rearranging, we will get FD equal to CD upon 2. Mark it as 9.2 equation. Now what is FD? FD. Or what is CD? CD. Okay. Now we will find what is FD, what is CD. Okay. For small angles, point D is very close to pole. Since we are using paraxial rays and angles are very small, so this D is lying very close to P. Okay, so this D is very close to P. So we can write, so that FD is equal to CD upon 2. We can write FD as FP. FD is approximately equal to FP because D and P are very close to each other. So FD is approximately equal to FP. And what is FP? It is the distance of focus from the pole, that is known as focal length, F. And we can write CD approximately equal to CP, which is equal to R. So this is the distance of center of curvature from pole, which is considered as radius of curvature r. So what is the final relationship? What was the final relationship? FD is equal to CD upon 2. So FD is F is equal to R upon 2. So focal length is half of the radius of curvature. Mark it as 9.3 equation. This relation only valid for paraaxial rays. Okay, that assumption of paraaxial rays will be used throughout the lecture. We are not considering marginal rays that are away from farther apart from the principal axis. So what is the physical significance of this equation or relation? Focal length is always half of the radius of curvature. This relationship holds for both concave and convex mirrors. It connects the geometric property with the optical property. What is geometric property? Radius. It is the radius of the spherical sphere from which mirror is cut. So this is the geometric property. What is the optical property? Focal length. Okay, it is not defined according to the geometry of the mirror. It is defined that how rays of light parallel to the principal axis will meet after reflection. So this is optical property. Forms the basis for mirror design in optical instruments. So let's have a quick recap. Human eyes can detect electromagnetic waves in the 400 to 750 nanometer range known as visible light. Historic understanding of light evolved from ancient Greek philosophers to modern scientists like Newton and Maxwell. Light travels at approximately 3 × 10⁸ in vacuum meter per second. Ray optics treats light as traveling in straight lines or in the form of rays when wavelength is small compared to the obstacles or apertures. Ray optics covers reflection, refraction, dispersion and image formation but can't explain wave phenomena. Wave phenomena will be explained in the wave optics by considering the wave nature of light. Laws of reflection state that incident ray, reflected ray and normal lie in the same plane and angle of incidence equals to the angle of reflection. Spherical mirrors can be concave, inward curve or convex, outward curve with key points like pole, center of curvature and principal axis. Cartesian sign conventions uses positive negative values to represent the distances and heights from mirror's pole. Principal focus is where parallel rays converge or appear to diverge after reflection. Focal length f equals to the half of radius, that is f equal to r/2 for spherical mirrors. There are some practice questions. What is the focal length of a concave mirror whose radius of curvature is 20 cm? If a concave mirror has a focal length of minus 15 cm, okay, it is given in the question, it is minus, but it will not be given in the question. What is the radius of curvature? You have to determine whether its focal length is negative or whether its focal length is positive based on the mirror. So for a convex mirror with radius of curvature 40 cm. Okay, for convex mirror, radius of curvature will be taken as negative or positive? Positive. Determine its focal length. According to sign convention, what will be the sign of focal length of concave mirror? If parallel rays after reflection appear to come from a point 25 cm behind a mirror, what type of mirror is it and what is its radius of curvature? So thank you. This is all about today's lecture.